Hello, in this video I will be using the algorithm developed by Rodriguez and Laus to organize a randomized set of data into clusters. So the significance of this algorithm is that we can use it to organize our data and to discover patterns in a data set that we might not be able to recognize with the human eye. So to make this code, we'll first import the packages that we're going to need. So we'll need NumPy in order to perform certain mathematical calculations. We'll be using the make subplots object inside the Plotly library for plotting our data in 3D. And we'll need the PIO function inside of the Plotly library to format our graphs. And we'll set our default settings for our graphs to Plotly dark. So the first step in this process is we'll need to generate an artificial data set that we can then organize into clusters. So first we'll use this numpy.random seed, and we'll use this for initializing the random number generator. So the reason we're using this seed function inside of the random Python object is that we want, for every time we run this model, we want to get that randomized data set, but we want it to be the same every time we run the code. So next we're going to specify our center points that we'll use as the center of our clusters. We'll create an array in Python. And we'll specify that we're going to have 4 cluster centers for this code. For each of these cluster centers, I'm going to give it an X, Y, and Z component. So now we have 4 points with 3 values within each point. So the X value, the Y value, and the Z value. So this will generate a 4x3 array. So we'll have 12 points within this array. So now that we have our cluster centers, we're going to specify how many neighbors we want each cluster center to have. So how many points do we want to be within each cluster? So for this, we'll generate a list of random integers, and we'll say that for each cluster it'll have between 15 and 19 neighbors. We want this list of random numbers of neighbors to be the same size as our cluster array. So we'll specify we want it to be C size. So since there were 12 points in our C array, there will be 12 points in our N array. So once we have our cluster centers and we have the number of neighbors there will be for each cluster center, we're now going to want to create an array that will hold the cluster centers and also all of the points around the cluster center. So we'll first create this empty array P, which will hold basically all of our data points. What I want to do is that this centers array is a 4x3 array. So we will want to add values to our P array for each row in the C array for all of the columns. So rows in C.shape. And because we're looking at each row in the C array, we'll want the first value in our C shape object, because C.shape right now will be 4, 3. So we went the 4. Every row in our C array. So for each row in our C array, we're going to add on to our P array. So we're going to append our P array. And we're going to generate a random integer, normal distribution. So the point around which we are generating a random point, referred to as loc, is going to be row I. So for example, if I equals 1, we're looking at row 1 in the array C, and we're looking at all of the columns. Our standard deviation for the normal distribution we're using to generate a random number will specify as 1. The size of the array that we're going to generate by appending P will be equal to, the number of rows will be equal to the number of neighbors which we get from our in array for whatever I is. So if I is 1, and we're looking at 0.1 in our C array, in I will be the number of neighbors for that first point. So if the first point is 15 neighbors, our size will be 15 rows, 1 row per neighbor. And for our C array, we have 3 columns for our X, Y, and Z points. So overall, this loop is going to generate. We can then concatenate our, in this case, 4 arrays, since we had 4 cluster centers. This way, we're combining all of our arrays for each of the cluster centers into one 2-dimensional array. So a couple things I missed there that first time. I forgot to specify that NumPy I'm referring to as NP. I also forgot to put the random Python object here before the random integer function. And I forgot to put here, I need to put range, because I'm basically saying if the shape of C shape 0 is 4, then I want to go from I equals 0, 1, 2, and 3. I also misspelled concatenate originally. So now we have a 2D array with so now we have a 2D array with 69 rows and 3 columns. So this means we have 69 points, and each of these points has an X, Y, and Z coordinate. So now that we have this data, we want to shuffle it so that we can use it to model what we would do if we were given a data set and we didn't already know the pattern of the data. So our random index would be NumPy inside the random library. We're going to use the permutation function. And we want to generate a list of numbers between 0 and 69. So we'll do NumPy, arrange, and we want it to be the shape of our P array. So we're saying here we have this random index, which we're going to get by generating this randomized list of numbers between 0 and P shape for our first column, which is 69 numbers in this case. So then we can set P to now be P with this randomized index. that, we now get our randomized set of data. Now that we have our randomized data set, we can first plot the data to kind of see what it looks like so we can visualize what we're looking for when we write our code for clustering our data. This figure, see our make subplots. Add a scatter, and because we have x, y, and z coordinates, we want this scatter plot to plot in 3D. So our x coordinates, we're using our data in our P array, and we want all of the rows in this array, but we're only wanting the first column because the first column of our array is our x values. The y values are the second column in our array. And our z value is the third column in our array. The mode we'll use for plotting our points will be text. And the text, again, we're wanting our points to be numbers between 0 and 69. So that will again be the shape of our P array. Okay, so here we have our clusters, and we can see that there are 3 clusters in the 3D plot. However, we're still going to generate the algorithm because the larger implications of this algorithm is that you could use it for cases where you couldn't just identify the 4 clusters visually, but rather would need the computer to tell you how the data is organized. So now that we've generated our random data set, the next step will be actually applying the algorithm. And the algorithm for clustering our data is based on 2 main parameters, which is the local density of each point in our data set, which is referred to as rho, as well as the distance between each data point and the nearest data point in the set that has a higher local density than the point we are examining. And this is referred to as delta. So the idea is that your cluster centers in your data set would have a large rho, meaning they would have a large local density. And they would also have a large delta because there'd be more space between cluster centers and other points that would have a higher local density than those cluster centers. So to get this distance matrix, we're going to, for every point in our P matrix, we're going to subtract the x, y, and z positions for every other point in that matrix. So if we expand our matrix, so we now have this P none / colon. So this is saying we have we're converting our matrix into a 2D matrix with 1 row and however many number of columns. And then if we subtract all of the rows for each column, using this subtraction, we'll be able to get the distance for the x, y, and z coordinates for each point in our matrix. And we're going to want to square that, get all positive numbers. And we can think of this now as we have our distance in the x direction squared plus our distance in the y direction squared plus our distance in the z direction squared. So if I sum all of these, if you take the square root of that sum of our distances in each of our directions, this will give us the overall distance for each of the points in our P array. So once we have this distance matrix, we're going to want to calculate our rho, or our local density, for each point in our matrix. And to do this, we're going to need a normalized distance, which we can use to compare with the distance for each of our points from one another. So if I create this standard distance, we can say that our standard distance will be the 5th percentile of our distance matrix. So now we can use that normalized distance when we're calculating rho. So now we can use this normalized distance to calculate rho. And the way that we'll do this, based on the algorithm used in the paper that we looked at in class, is we'll have this ratio between our distance between the point that we're looking at and every other point in the matrix. And if we take this to an exponent, this will mean that, and add this up, basically for us is that if the ratio between the distance and the normalized distance is very large, so meaning that there is, so basically what this is telling us is that if the overall distance for a point is a lot larger than the normalized distance, then this means that the local density will be much smaller, meaning that that point won't have as many neighbors. However, if the density is pretty close to our normalized density, then this tells us that the local density for that point is higher. Calculated rho. In order to calculate delta, we'll need to know that for every point in our matrix, we'll need to know which other points in the matrix have a higher local density than that point that we're looking at. So what this rho ij tells us is that if this first row is bigger than the second row, then that point has a higher local density than the point that we're looking at in our array. So we can then use this to calculate our delta, as delta will be the minimum distance between a point and the nearest point with a higher local density. So if we want to minimize our distance between the point that we're looking at and the point with a higher local density, we can say, so when rho ij is true, that means that that point has a higher local density than the point we're looking at. So that would mean we want the delta to be as small as possible. When ij is true, though, it has a value of 1. So we want to flip this so that we can get a minimum distance. We'll use NumPy logical not, which means that when this rho ij is true, the value will actually get flipped to a 0. So then when we add our distance, we'll get that delta between point I and point j is just the distance between those 2 points. However, if a rho ij is false, meaning that the point j has a smaller local density than point I that we're looking at, then this will mean that numpy.logicalNot rho ij will be equal to 1. And this will cause the delta to have a larger value, which would mean that there's a larger distance between that point and the points around it that have a higher local density. And we can compound this fact to make it more dramatic by multiplying by the maximum distance possible from our distance matrix. So now this whole line will calculate delta for each of our points in our matrix, and we'll see that values that have very high values or very high local densities will have smaller deltas, except in the case of cluster centers, whereas points that are farther away from other points of higher local density will have larger deltas. The points in the center of the cluster center, or the points that are the center of the clusters, will have the largest deltas because all of the points around them have a smaller local density. So now that we've calculated rho and delta, we're now going to want to specify the indices of our values, our closest values that have a higher local density for each of our points. So to do this, min function, we're going to use argmin. So this will work for getting the point with the nearest higher local density for most of our points. However, for the point in our data set that has the largest or the highest local density, we'll have to specify the local density instead. The just value in our row, and then we can put that the delta for the value in our data set that has that row max. Rather than calculating row, or rather than calculating delta using our value up here, we'll simply specify that delta is the maximum distance in our data set. So now this tells us that our delta for our value with the highest local density will simply be the largest distance in our distance matrix. And finally, now that we've calculated rho and delta for all of our values, we can now calculate delta rho by simply multiplying delta So now that we have our delta rho values, we're going to plot these values so that we can figure out which of our points in our data set are cluster centers versus which are surrounding cluster centers. So first we're going to sort our delta values into a delta index, or into an index. All the values in our delta rho matrix. And we can add a scatter plot. X values will be the size of our delta index. And our Y values will be for each index in our delta index matrix. We want to find the delta rho. Okay, so here we have our points, and we can visually see that these first 4 points have much higher row delta. So they have the highest local densities, and they also have the largest distance to the nearest point with a higher local density. So now we need to figure out how we can differentiate these first 4 points from the rest of our points in our data set. And so the way we will do this to determine which of our points on this plot are cluster centers versus which points are surrounding the cluster centers is that we will take a line from our first point to our last point and find that this corner point over here will be the point that has the largest distance to that point between our, or to that line between our first and last points. So to reiterate, we're finding the first point in our data set that is not a cluster center, and we'll do this by finding the longest distance to a line drawn between our first and last point on this graph. A function, call it me, because of the shape of the graph is bent at this angle. Oops. Values from 1 to the size of our values, so it'll be between 1 and 69 for this data set. And our y value will be the actual delta values for each of the points in our delta index. So we'll want to take our delta size array and our delta array and concatenate this into one data array. We want to first get the line between this first point and this last point in our chart. So the last point on our chart, on our chart will be 0. The last point on our chart will be -1. We then want to normalize this vector from the first to second point. So now we'll want to get our normalized line. So to do that, we'll divide our vector by the absolute value of this. So we'll do square root of sum of our squares. Now that we have this unit vector, we want to get the vector between this first point and each of the points in our data set. So we'll call this a normal line or normalized line. This will just be for each of the points in our data set, we're going to subtract that first data point. And once we have this, we can then get the distance between each point on in our data set and once we have this normal line vector, we can then get a projection of this line between our first and last points to whatever point we're looking at. So for example, if we were looking at this first point in the corner here, we found the unit vector going this direction. We also found the vector going to the point we're looking at. So now we can get a projection that will take us to around here on our chart. Projection will equal our line expanded into a 2D array times, or our unit vector, times the dot product of normalized data and our unit vector. Once we have that projection, we can then calculate our perpendicular vector, which will be our maximum distance between this line and our points in our data set. Once we have this, we can calculate the magnitude of that vector. So our distance has before distance we're adding up the squares of the individual differences, taking the square root of that. So once we have this function now for separating out our cluster centers from our non-cluster centers, we now need to apply it to our data set. We can now use this to calculate the number of in clusters in this particular data set. This will be size of our delta array second value is each delta value in our delta index. But if this returns something, we want to get this corner point in our chart. We want to maximize that. So this is so our unit vector is the normalized line. Our normal data is this value, and those are two separate things. So there's norm line, and then there's also norm data. Okay, so there we go. So now we've got 4 cluster centers, which we saw in this table, or in this chart up here. So now that we found the number of cluster centers, we're now going to separate our data into cluster centers and non-cluster centers, and associate each of our non-cluster centers points with a cluster center point. So we're going to start with our cluster centers and slowly work our way out until we've captured all of our data. So we're going to make a cluster matrix, which will be same size and type as our P matrix. So for all the rows, we'll be looking at first column our P matrix. So that'll give us a cluster matrix with however many rows in our data set and 1 column. Now, for now, we're just going to fill this matrix with all -1 values. Type in here will be integer. So now, since we already have our in clusters, we can say that the delta index for all of these clusters gives the delta, so this gives the range. So since we had 4 clusters, we have the range 0, 1, 2, and 3. So for clusters in for clusters at this index, so clusters for all of our delta indexes for all of our clusters that we counted will now belong to one of these in clusters from 0, 1, 2, or 3. So in this line here, we're giving the index for the clusters that are for the points in our cluster matrix that are the cluster centers. So they're between 0, 1, 2, and 3 for this data set. Now we can say that our index for assigned values will be wherever in this cluster index we have a value that's greater than -1. And we want this for we want to specify we're indexing at 0, so that way we don't get a tuple since this cluster is a 2-dimensional array. So now we can say that the number of values that we've assigned to this are assigned the size of our assigned index. So we now have our index for our assigned values, which are our cluster centers. So now we need an index for our non-cluster centers. We use this numpy.setDiff 1D function, which will return values that are unique to the first argument that we put into this function, but not the second function. So the first value will be range of values, including all of our data set. We have our delta index. In clusters, so that's giving our cluster centers. So we want values that are unique to this first section but aren't cluster centers, and that will give us our indexes for our non-cluster centers. So we had, this is correct, we had 4 assigned values already because we had 4 cluster centers. Okay, so now that we've separated our cluster centers and non-cluster centers, we need to now sort our non-cluster centers into groups by our cluster centers. So we're going to be sorting as long as assigned index size is greater than 0. So as long as we still have values that are unassigned, we'll keep looping through this while loop. So we want to get both the delta index. So that was our numbers between 1 to the size of our data set. And we also have our cluster index. Tell us which cluster group each data point belongs to. So we're going to use this NumPy non-zero function, which will return a non-zero tuple. So we'll get our delta index and cluster index. So for each point in our data set, we want to find the data points for which the nearest higher density index highest density index for each of our non-cluster centers. So for each of our non-cluster centers, we want to find the points whose nearest higher density index is equal to So we have our points. We're trying to find the points around our higher density points for which the nearest higher density is the points that we've already assigned. And we have our delta index and cluster index. We can then say that in our cluster matrix, non-cluster center index for that delta index equal to the cluster index for that already assigned index. So if we found that a point in our non-cluster index had a point that was its nearest higher density index that was one of our center clusters, we could then say that that data point. So for example, if during this first run we found that one of our points had a nearest higher density, or it had a nearest higher density neighbor that was cluster center 2, this would then mean that that data point would get sorted into our cluster 2. And now, finally, we can update our assigned cluster center index. So finally, we can plot our sorted data. So just as before, we'll make our subplots. We can use for showing the different clusters we've sorted. And the only thing we'll change here is that we want our text font color equal to colors, and an easy way to organize our colors by clusters. We'll pick clusters +1. So for example, for cluster 0, cluster +1 is 1, so we'll get cluster 1 will be, or cluster 0 will be blue. There's our cluster centers, or our data separated into 4 distinct clusters. So the larger applications of this project were that, in this case, while we can visualize the 4 clusters of our data in this plot, if you were working with a larger data set, which had more than 3 dimensions, you could use this algorithm to separate your data into clusters in order to find patterns and elucidate information from your data without necessarily being to visualize it with the human eye.